Hello again and welcome to another review session for your final exam in Calculus 3208. And we're finishing up. This is our last video on applications of derivatives, and we're looking at economic applications of optimization today. So our last video for Unit 5. So let's move along. We've got minimizing cost of materials, maximizing revenue, and maximizing profit. There's three ways we can use calculus and optimization problems to solve some economic application issues. So let's have a look. Optimal economic decision making. Fun stuff, huh? So the first thing we want to be able to do is minimize costs. And when we do that, we have to be able to take a situation for a business or whatever and figure out a cost function. All right. And once we have our cost function, we'll do that in terms of some variable x, then we would use our ways of finding the global minimum or the absolute minimum for that function to minimize the costs. And the next thing we look at is revenue. So revenue is defined as the quantity of things that you sell, if you're selling stuff as a business, multiplied by the price that you charge for each one. And that makes sense. So revenue is basically just the money that you take in from your sales. Sometimes we call the quantity the sales function, and sometimes we call the price the demand function. But either way, it's how many you sell multiplied by how much you charge for each one. And then for profit, well, profit is your revenue that you take in, and then you have to subtract how much it costs you to get there, so your costs. So profit is revenue minus cost. So it's a profit function, and it's a revenue function, and it's a cost function. So sometimes we'll even see profit written as capital P of x for profit is going to be equal to lowercase q of x, your quantity, times your price, and then subtract your cost function. So we'll get into one of those later too. So let's see if we can do an example of each of these. So the first one is a cost function issue. A closed top box. So this person or this company is constructing a box, but they want to minimize their cost to do it, not necessarily their materials. So a closed top box with a square base is to have a volume of 10 meters cubed. So I'll do my best to rough out a diagram for a box with a square base. So it's going to look something like this. And we know that the base of the box is square, so we can call it x by x. The height is not necessarily the same thing. So it says we want to minimize our costs, and the different surfaces have different prices, so we're going to write a cost function here. And I'm going to have, let's see, the sides like these ones, I'm going to have 4 of those all the way around, and they'll be identical. So each one of those is x times h for its area. So I got 4xh, and the sides cost $2 per meter squared to make. So I'm going to say 2 times 4xh will give me the cost to manufacture all 4 sides. Then it says I have to add the base costs $4 per meter squared to make. So I've got 4 times the area of the base, which is x squared, plus the top is only $1 per meter squared to make. So I've got $1 times x squared for that one. So I'm going to simplify a little bit if I can. My cost function is going to be 8xh plus 5x squared when I put it all together. So there we go. Uh-oh, too many variables. We've got to get a secondary relationship. We know the box has to have a volume of 10 meters cubed. So volume is going to be our secondary relationship this time. So the volume, which has to be 10, is going to be equal to x squared times the height. So length times width times height. And so if we want to replace the h, we can say that h will be equal to 10 over x squared. So when all is said and done, our cost function is going to look like 8 times, instead of xh, we're going to say x times 10 over x squared plus 5x squared. So given a list of constraints and rules and all kinds of things, we're able to figure out that if we take 80 divided by x plus 5 times x squared, where x is the length of the base, then that'll tell us how much it costs to make that box. All right, so we want to minimize the cost to make the box, so we could make x as small as we want or as big as we want, but obviously it's going to be somewhere in the middle there that we're going to get our optimal cost. So we're looking for critical values really. So c prime of x, the derivative of 80 over x is negative 80 over x squared, plus the derivative of 5x squared is 10x. All right, so we're going to let that equal 0. So 0 equals negative 80 over x squared plus 10x, and then we're going to try to solve for x. So I'm going to get 80 over x squared equals 10x. So 80 over 10 is 8, and that's equal to x cubed. So x will be the cube root of 8, which is 2. So if we let x be 2 meters, then we will get the minimum cost to build the box. They don't ask us what that cost is, they want the dimensions. So we got x, we've got to tell them h2, so that h is going to be equal to, from here, 10 divided by x squared, which is 4, so that'll be 2.5. So the minimum cost to build this box will occur if I let x be 2 meters along the bottom and the height of the box be 2.5 meters. Good question. That's a fun one. All right. Now we're going to get more complicated. So Shelby, whoever Shelby is hired to buy a new, or hired by a new sporting goods store in Gander, lovely town Gander, to do market research on the sales of Flyers jerseys. Okay. So currently the jerseys sell for $50 each, and they're selling at a rate of $100 per week. Okay, so the current price is $50, and we're selling $100 per week. Shelby determines that sales would decrease by 2 jerseys for every $5 increase in price. So we're going to invent a variable here. We're going to call it x, and we're going to say x is going to be the number of times we increase the price by $5. This is not the only way to solve this problem, but it's certainly the easiest in my understanding. So what we have to do is we want to maximize their revenue. So we need a revenue equation, remembering that revenue is equal to your quantity function, or sometimes called your sales function, times your price function, P of x. So we need both of those first. So the price function, P of x, is going to be equal to, well, we were selling them for 50, and we're going to raise the price by $5 x times, so the price will be 50 plus 5x. And then our quantity function, Q of x, is going to be, well, we were selling 100 per week, but every time we jack the price up by $5, we're going to lose 2 jersey sales. So we're going to say 100 minus 2x. Alrighty. So with that, then, we can write our revenue equation. So revenue as a function of x is going to be equal to 100 minus 2x multiplied by 50 and 5x. So the revenue is going to be, let's see, that gives us, doing some quick algebra here, minus 10x squared plus 400x plus 5,000. Okay, so we want to find out the maximum, or what value of x would give us the maximum possible revenue. So I guess we could say we don't change the price at all, or we could say that we could change the price as many times as possible. But either way, I don't think the endpoints are going to get us to a maximum here. So we're going to look for critical values. So r prime of x is going to be negative 20x plus 400. All right. So we let that equal 0, and we get 20x equals 400. So that tells us that x is going to be equal to 400 over 20, which is 20. Wow, we're going to have some expensive jerseys here. The question does not ask us what is the maximum revenue. It asks us what price should Shelby recommend the store charge in order to maximize the revenue. So that price at 20 is going to be 50 plus 5 times the 20 times we change that price, and we're going to have a price of 50 plus 100. So we're going to sell the jerseys for $150. We're going to lose some sales that way, probably a nice few, but it still gives us our maximum possible revenue. Okay, so let's see what's next on the agenda here. Okay, we've got another problem coming up, and this one is going probably, oh, it is a profit function. Great, so these are the toughest of all. All right, put it all together. The manufacturer is selling an average of 1,000 flat screen televisions each week at $450 per TV. Market research indicates that each $10 price reduction increases sales by 100 per week. We'll sell lots of TVs. The factory in which the TVs are made assesses its operating cost at $68,000 plus an additional cost of $150 per TV sold. And all this happens in a week. That's a lot of money in a week. Determine the manufacturer's maximum weekly profit under these conditions. Okay, so I guess we're going to be consultants for a TV manufacturer here. Let's see what we can tell them. So we're going to have to get the whole 9 yards here, because profit, remember, is equal to your revenue, which is your quantity multiplied by your price, minus your cost function. And often, cost depends on your quantity as well, which is the case here. So let's figure out, first of all, how many are we selling? So right now, we're going to sell 1,000 flat screen TVs, but we're going to reduce the price, and that'll increase our sales by 100 per week. So we're going to say X is the number of times we reduce the price, just like we did in the last problem. X is the number of times we change things. So we're going to add 100 times X to that. Then our price function, we were originally selling our TVs at $4.50 a piece. And what we're going to do here is we're going to reduce the price by $10 X times. So minus 10X. Okay, so we've got our quantity and our price. We just need to figure out our cost function now. So the cost function here, they tell us, weekly costs are flat of $68,000. That's probably your overhead. And then from that, we have to add an additional cost of $150 for every TV we sell. So 150, how do we know how many TVs we sell? We don't, but we do have an expression for it already. So it's 150 times the quantity that we're actually selling. So then our cost function becomes 68,000 plus 150 times 1,000 plus 100x. So that's a lot of money for costs. Let's see if we can do some quick algebra to reduce all that down. I'm going to skip a step or so here, and we get 218,000 plus 15,000x. So 280,000 plus 15,000x is our cost function. So now we can finally write our profit equation. The profit equation here is going to be Q, which was 1,000 plus 100x times our price function, which is 450 minus 10x minus our cost function. So we're going to take away our costs, which are 218,000, and distributing that negative minus another 15,000x. All right, so we've got this crazy thing. And I'm going to save you the gory details of the algebra. If you want to take a minute and pause your video and work through it, you can. But I'm going to simplify this all in one fell swoop here. So I get my profit equation to be negative 1,000 times x squared plus 20,000x plus $232,000. It's lots of money we're talking about here. Okay, so I don't have to change the price, so x could be 0 or x could be as big as I want it to be until I got down to a point where I wasn't making any money anymore. But we're going to look for critical values here. So P prime of x is going to be negative 2,000x plus 20,000, like so. So we'll let that equal 0. So if P prime of x equals 0, then we have 2,000x equals 20,000, which means that x is going to be equal to 10. So that says we should take $100 off the price of each TV, doesn't it? Because we're going to reduce the price by $10 10 times. All right, so now they do ask us, however, what is the maximum weekly profit that this manufacturer can earn? So let's see. Profit at X we have already, so we're trying to find profit now when X equals 10. So we want the profit at a value of 10. So that's going to be negative 1,000 times 10 squared plus 20,000 times 10 plus $232,000. All right. So if you're handy with numbers, or if you have a calculator, you'll get an amazing profit weekly for this firm of $332,000 per week. Wow, and that's profit. Man, I'm in the wrong business. I should give up this math stuff. Okay, now it's your turn. A video game designer has been selling blah, 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 600 games. This is a good question. It's a maximum revenue question, so just have a flick back if you need. So take a look. We've got cost, revenue, and profit, all that. This is a revenue one. So here's the solution, and you can work it all out, and you get that for a solution for it. So hopefully you're getting the right answer. And let's look at all the things that we talked about today. We talked about 3 types of economic situations: when we want to minimize our cost, when we want to maximize our revenue, or when we want to maximize our profit. And when we use the methods that we already developed for solving optimization problems, we can determine the optimal value of the thing required. The only thing that's a little bit different here that you have to make sure you get in your head is you have to know the situations and how to set up the equations for each of those 3 things and what they mean. Hopefully that was a little bit helpful for you, and hopefully your studying is going very well and that you're going to ace that calculus exam. If you have any questions, post them on D2L. Thanks, and good luck studying.